Donc on va passer donc au prochain orateur, qui est oratrice, Pascale Lherminier, qui est chercheuse à l'IFREMER, au LOPS et à l'IUEM à Brest, qui va nous parler des observations. Observe variability of the Atlantic Meridional Overturning Circulation since 1993. Merci, Pascale.
Oui, désolée de parler en anglais du coup, mais c'est vrai que si on veut avancer en sciences, il nous faut une langue commune. Donc, on n'a pas pris l'espéranto, on a pris l'anglais, c'était plus simple. Et we have people invited here from different countries, not necessarily Anglo-Saxon countries. So we try to communicate with them and make the day more interesting also. So today, today I was honored to be invited by Mr. Edouard to talk to you about the observation of the Atlantic Meridional Overturning Circulation since 1993, since it's my research of topic at IFREMER in Brest. So this talk is, of course, more of a communication, larger audience communication talk, but lots of slides you will see are from people from our team and from the technicians who are very important for all the observation part, and also some contribution of Gerald McCarthy, some slides of that he did. So first I will do a short introduction of ocean and climate and why it is so important to understand exactly the dynamics of the climate. So I won't come back so much early than you did. I will just come back on the last century when we emitted lots of carbon dioxide in the atmosphere, and it increased the greenhouse effect. And so what I wanted to where is it? You have a pointer here? Or it doesn't matter? See something? No. What I wanted to understand, make you understand is that the ocean actually captured 93% of the excess of heat. And this is huge, actually. It only warmed up by 0.15 degrees because it has a very high heat capacity. So here is the heat content of the ocean over the first 2,000 meters. And it, as you see, it increased by a tenth of a degree, a bit more. And this heat is obviously not only at the surface, because it's also in the most of the heat is the first 300 meters, excess of heat. But you can see that the heat already came into the deep waters down below 2,000 meters, which is complex to measure. It's not homogeneous, as you've seen. This is the 2021 average compared to the 1950 to now average. So it's an anomaly chart, and you can see the cold blob, as you say. It's still here, but it's decreasing a bit. And lots of warming are in the subtropical gyres here. And what is important also is that there is a big anomaly, so in the North Atlantic, so we can expect the storms and the hurricanes to be even stronger because it takes their energy from the ocean heat. So not necessarily many more, but more destructive, definitely. What is the ocean acidification in the latest year? Well, you know that carbon dioxide decreased in the atmosphere, so it penetrates and dissolves in the ocean. And what is important is that there is a bistable equilibrium between the dissolved CO2 and the carbonates, and with the bicarbonates. So it's a double chemical equilibrium here. And what is important to understand is that this bicarbonates molecule is actually at the base of the shells of many phytoplankton and zooplankton species. So if we reduce, like here, the bicarbonates molecules, then we fragilize all the shell populations, all the bivalves and so on. Plus many others adaptation. Once again, the anthropogenic carbon is not homogeneously scattered? No, doesn't matter. Réparti? Huh? And in the North Atlantic, it's been particularly huge in terms of storage, and you will have several talks this afternoon about this, so I won't come back on this aspect. But still, since I'm talking about the Atlantic Meridional Overturning circulation, this circulation is responsible for the penetration of the carbon dioxide signature into the water column here near Greenland in the Lherminier Sea. It's a sea that is observed by many countries because in the day after tomorrow, the film, we know that many signals are here, and this is usually quite a precursor in this area. But what you can see here is that we've been observing this point for 20 years now, and this is the depth here, and you see the red is the carbon dioxide penetrating into the water column as time goes by. And now it reached, in 2018, it reached more than 1,500 meters. And this makes actually the deep corals in danger because this acidifies the water. So now I will come back on some historical background of the ocean observation. You've already had quite a few with Edouard, and I will just remind you that the first real oceanographic cruises that I know of, really ships going out for measuring the ocean, and not by opportunity, was the cruises of the Challenger in 1873 and 1876. Much later, well, there was a lot of steps, construction of oceanographic ships and so on. But I wanted just to come back on this chart that I like a lot, because we already see in the North Atlantic, so the subtropical gyre here, and you have this, what we call the subpolar gyre because it turns, and the Gulf Stream is here, and you can see that it's quite nicely drawn from here. And the North Atlantic current that you see is actually the part of the Gulf Stream that will go up, and it will go until the Arctic. But part of the Gulf Stream recirculates and creates the subtropical gyre here. So this chart, at the same time that in the Second World War, we made a lot of progress. Yes? Oh, sorry. Yes. Excuse me. So at the same time that this chart was drawn because we made a lot of progress during the Second World War. Henry Stommel, who was a very famous oceanographer, probably, and he put a lot of basis in our discipline. He said something that for me it is inspiring. He said basically that we do not deduce immediately the machinery of the ocean without the help of the insight, which we obtain from a mental image that we invent ourselves. And observations gathered in the real ocean are used to modify and correct this image. And this is really, for me, the heart of our research, because like in astronomy or in some science of very small elements, we need a lot of imagination to progress. But the imagination and the theory is not enough. We need also to go out to observe the reality and come back and confront this to what we've mentally imagined. And this is a process of back and forth. So another revolution of the observation of the ocean was in 1980, when the satellites began to observe the ocean, and particularly here the temperature of the Gulf Stream, for example. And then in the 90s, for the first time, there was a coordination between the different nations of the world to create the World Ocean Circulation Experiment. So the objective was to map quite rationally the ocean to be able to collect CTD data, to collect temperature and salinity data, and draw a map of the mean ocean state. So here you can see that, and I need to be a temperature, let's say a temperature section across the Atlantic from Greenland to Antarctica here. And you see that the temperature of the bottom waters is around 2 degrees, and the surface can be up to 30 degrees. So this has been done over all those sections during the 90s. And then in the 2000s and later on in 2010, we tried to continue our collaboration and try to continue to coordinate. And so in France, the French and Spanish contribution is the Ovid section. And it's called A25. It's Ovid for Observatoire de la Variabilité interannuelle à décennale en Atlantique Nord. So it's been a hydrographic section that have been carried out every 2 years in France and in Spain. So we, from the beginning, from 2002, we collaborated with our colleagues of Vigo, and they are more focused on the carbon cycle, and we are more focused on the physics. And it consists, where is an oceanographic cruise? Well, maybe some of you don't know, but it consists of stopping every 30 or 50 nautical miles. We stop and we put probes into the water down to the bottom to recover both some samples of seawater at different depths and temperature in continuous profile. Another big step forward was the Argo program. So it's profilers that are autonomous and drift with the currents, and every about 10 days, depends on the programmation, but more or less 10 days, they come back to the surface after profiling between the surface and 2,000 meters, and they send immediately to land profiles of temperature and salinity. It was a revolution because up to now we had only scarce data in the ocean, and suddenly we were able to collect 2 million profiles in 20 years. So it's pretty much like the balloons in the atmosphere. It's fundamental to get a better reality, and that's where the numbers that you saw at the beginning of the talks come from, the heat content and all this. And we've been able to do that thanks in many ways because of this network. However, because they are drifting without being monitored, they drift with the currents, some regions that are divergent for the floats are still under samples. And also all the boundary currents cannot be covered. So even if it's great, it's still not enough because boundary currents carry a lot of information, as you will see later. So what do we routinely measure? Pressure, that gives us depth. Temperature, conductivity, that gives us salinity. Although it seems obvious, but it's not that obvious because salinity is not an obvious parameter to measure, I tell you. And currents. We measure currents by Doppler effect. And then we also measure for biogeochemical variables, dissolved oxygen, macronutrients like silicates, phosphate, nitrates. We also measure everything that is in combination with the implied in the carbon cycle, which is the pH, the alkalinity, and also the organic and inorganic dissolved carbon. We also measure transient traces that you saw some results with Edouard, and like rare earth elements or isotopes and freons and stuff like that, that give us actually mostly information on the age of the water masses. And then we also measure biological variables, but it's not my part, so I won't talk a lot about it, but it's a chlorophyll and stuff like this. Here is an example of a profile we measured in the Iberian abyssal plain. And you see on the left the temperature, and then at the right the salinity, the density, and the oxygen, dissolved oxygen. So those are measured continuously from the surface to the bottom thanks to a CTD. And I like this profile because it's a profile which shows at 10,000 meters deep the tongue of the Mediterranean water. And here, which is more salty because the Mediterranean is actually an evaporation basin. And here you have not such a big signature in temperature, although there is it's a little colder, so that the density keeps increasing with depth. Because in density you will have always dense water below the less dense water. And Mediterranean water here also characterized by a minimum of oxygen. So our job is actually, when we observe the ocean, to understand where the water comes from and how they've been created and what are their signature, because it gives us a lot of information on the circulation and how the ocean works. Here are some images of all the instruments we use: the ADCP, the Argoprover, the Rosette. This is the profiles I showed you just before comes from the probe that is mounted on the Rosette, and this is the thing that we put in the water down to the bottom. So we use Doppler current meters here. We use also moorings, gliders. Gliders are like Argo floats, but you can steer them, but they are much more expensive. But you can control them like a video game with your computer. And then you can also measure turbulence. We are able to measure mixing and diffusivity, although it's not easy. So this is the instrument. And now that I did present you the autonomous platforms, so and the platforms where you need to go out at sea, I would say that they complement each other, because we need both of them, because when you go out at sea, you can have a greater precision. We work in laboratories. You can have greater depth and many more variables from the samples. So, but we need all the time to optimize the ocean observation network, because otherwise it's so expensive that we need really to be efficient and not duplicate the efforts. So we go now that you've seen all of the instruments and so on, to the ocean circulation. I didn't think, what time is it? Okay. Edouard already showed you the main currents, surface currents that we know pretty well. Actually, we've known them for quite a while, several centuries, because the ships encountered them, so they knew they existed. And they are mainly wind-driven, those currents. But then from below these warm currents, you recognize what Edouard introduced as the meridional overturning circulation. And even the North Atlantic is mostly my focus, because even if it is true that some processes pour the MOC from the bottom, you have actually strong processes with the storm route coming here that remove lots of heat from the surface of the ocean, and that deepens. So the waters get denser and comes back at depth in the ocean here. So it's a very simplified sketch that has defaults, but still, it helps to understand how much all the oceans are connected. So 3 regions on the planet are really active in terms of convection. This is the Nordic seas and the Lherminier Sea. The Labrador Sea here, but you also have the Weddell Sea down there in the Arctic Ocean, which creates very, very deep water. This is an animation that helps to the story of a water parcel over 800 years. So the water parcel you see here has the color of its depth, and it's been released near the Indonesian Straits, and you can see all the paths they do, and it emphasizes how much all the oceans are connected. And as I told you, this little parcel came even in the Arctic and gets denser and comes back at 5,000 in the model at 4,000 depth to the tropics. So the ocean is our climate regulator because it distributes the heat excess received at the tropical regions towards the polar oceans. But the order of magnitude of the heat it transports has always amazed me. We are talking here about, 10 to the 15 watts. 10 to the 15 watts is 200,000 nuclear power points. I mean, this is just very difficult to apprehend. It's so big. And yes, something else here. What is interesting is that why is the North Atlantic, which is mostly so much important? Well, it's because finally, in terms of it's the hazard of the topography. You have room here for water to go through. And this is not true at Bering Straits, where it's very narrow and very shallow, so it cannot go through. So it's the North Atlantic is the place where it is very, very effective because of the coast and how things are, how Earth is his emerged Earth is réparti. Interior ocean circulation. So to look at large-scale stationary equilibria far from the land, we can simplify a lot the equations. It begins what you see here, which is a balance between the pressure gradient forces and the Coriolis force. The Coriolis force is an inertial force linked to the rotation of the Earth. So, like in the atmosphere, when you see depressions and anticyclones on the meteor maps, it's exactly the same in the ocean. You have regions with depressions, which are cyclonic circulations, and regions with bumps that creates anticyclonic circulation. And the balance, so the balance is reached when the currents are perpendicular to the pressure gradients, really exactly like in the atmosphere. What is really interesting for our science is that actually the elevation of the surface of the sea, which is not flat, gives us information on the currents integrated on the water column. So we are now able, from satellite, to measure the altitude, and this is a science called altimetry. So we are able to measure how much the sea is elevated. And we use it a lot. For example, a zoom in the North Atlantic. Here is an altimetric chart of the North Atlantic. And you can recognize, like the map I showed earlier, the subpolar gyre, which is a depression. It's a cyclonic circulation. And you also recognize, although it's more fuzzy, the subtropical gyre with the Gulf Stream here. As it was already told, unfortunately, the journalists keep saying about the Gulf Stream that it's gonna cease. But it's not the Gulf Stream that is gonna stop. It's the North Atlantic current that is probably may slow down in the future. Because this North Atlantic current, which is important in the Meridional overturning circulation. But obviously, it would be so much simpler if we just had just little branches like that, and we go through and we measure it. But when you put the whole circulation and try to really catch different branches of the different currents, then in red here you have the surface warm water. In blue, dark blue, you have the deep water. So this is the lower limb of the MOC, the one that comes back to the tropics, like along the western boundaries. And you also have some more intermediate waters. Here, the Labrador Sea water that is formed by deep convection. I will come back to this later. And the Mediterranean water. You saw one of the profile I showed you was somewhere here. Profile of salinity that you showed you saw earlier. Oh. So here on this kind of map, the subpolar gyre is much more fuzzy. It's much more difficult to guess where it is, because it's composed of lots of currents that have different stories. But when we come back to the general sketch, then here how we can represent in 3D in the North Atlantic, the Atlantic Meridional overturning circulation. And so you have to hear the section, the orbit section I told you about. It's what we could reconstruct of the temperature of this section it was in 2002, this one. And with the warm water of the Gulf Stream coming from the subtropics here, and the very cold water coming back from the Nordic seas. And actually all this here in dark blue has been ventilated and recreated in the winter before by convection in the subpolar gyre. So the very deep branch comes from the Nordic seas, and it overflows at the Denmark Strait and at the Faroe Channel here between UK. And but some of the lower branch is also not so deep in this area, and it comes from the mixing processes that mainly occurred in the Lherminier Sea and a little bit in the Iceland Sea. So this is the AMOC in the North Atlantic, a sketch of the AMOC. Why measuring the AMOC? Well, as it was shown earlier, most of the models say that it will decrease in the future because of climate change, and if it decreases, it modifies our climate necessarily, so because the ocean is so important to bring this heat from the tropics to the poles. Did it decrease? Did we observe that it decreased? Well, spoiler, not yet. Not in the observations, at least. The observation of the water column. I'm not talking about the observation about the sediments, which show that accidents, as we saw, occurred already. But up to now, I'm not convinced we observed it. So first, how do we quantify the Atlantic Meridional circulation? I mean, this is a huge balance of many currents. So what are we doing? Well, when usually we consider a zonal section, a zonal that's across the Atlantic, and then we integrate all the velocities that are across this section, and we accumulate all this, and it gives us the amplitude of what is going north and what is going south. Well, it's a rate, and it represents the rate of transformation of light waters into deep waters. So it's a transbasing integrated values, and to be really clear, it's just the sum of velocities. You don't have to see that in another way, complicated way. You take the upper branch that goes to the poles, and you sum the velocities. So you have cubic meters per second, and it gives you a transport. And you do the same. Sometimes we do it from the bottom. You do the same with the return current. You sum all the components of the velocities of the currents that comes back to the south at depth, and you have the lower limb of the MOC. So you measure either the upper limb or the lower limb of the MOC, going northward and southward. But this value depends on latitude, of course, and then time. So in models, you will see that they take the maximum of this over the whole ocean. Well, the problem in the ocean, if we could do that, if we had this kind of array of measurements, that would be cool. We have actually the technology to measure the velocity everywhere in the ocean. We have Doppler profilers for currents. We have temperature and salinity probes. We could put this everywhere in the ocean. And we would be able to do like models and take the maximum of this and say, this is the AMOC. But this is not possible. This is not, when you spend 1 year to try to fight to have money for deploying just 3 moorings with current meters and temperature and salinity, and then you fight again against the elements to recover those moorings and those data that have been in the water that you had no news for 2 years. When sometimes you see your instrument falling in the water full of data and you will never have them. So you understand that this kind of plan is just totally out of reach. So we have to be clever. Obviously, we have some solutions, and particularly we have in our hands this marvelous thermal wind equation, which solves a lot of things. I will show you later some illustrations of how it helps. So, to come back to one of the tools we have, which are the hydrographic sections. Here is, for example, a recent study that took back all the data of zonal hydrographic sections we had since the 90s. And it combined all this by decades to see if the MOC actually varied during the last 30 years. And they used some inverse modeling, so to take into account several constraints so that you don't have accumulation of mass or salt somewhere. So we use constraint in addition to the measurements so that the circulation we obtain is more realistic. And also it has by inversing matrices, we have also access to the errors. And here is one of the results for the latest decade. And what you see is, you don't see the numbers, and that's normal. I don't see them either. But I wanted to show you, so this is the from the south to the north, and this is the density values here. So you have the surface here, and the bottom here, and here. This is the latitudes. And so you observe here what we call the MOC, the Meridional Overturning circulation. And you can also see secondary circulation that actually played a much bigger role in some paleoclimates. You probably will know about it soon. And this water comes from the Antarctic Ocean, and it's called Antarctic bottom waters, and it comes back to the North Atlantic, and about at 30 north it stops, but it's upwells because of the bathymetry of the basin. The water upwells and comes to feed the deep branch of the Atlantic meridional circulation, which complicates a little the matter when we want to measure only this one here. Okay. So that's the first tool we have, hydrographic sections, and we really get organized to have them. Then we are also able to measure at gateways. Gateways, this is very much more easy because it's less large, and even in the Faroe Bank Channel here, where you have the overflow of the Iceland-Scotland overflow water, we call it like this. Actually, after several tests, Hansen and Hosteris wrote that finally we could pretty much monitor this current with only one mooring and one current meter. So that's very efficient. And in the Denmark Strait water also, this is very narrow, so we are able to monitor it. And so that's extremely powerful when you want to do budgets of the ocean, like we do between the different sections on the seals here, for example, because we have constraints of the transport. So what you see here for the overflows is also true. Well, it's not really true for the North Atlantic current. We cannot measure it so easily directly because the North Atlantic current is scattered between. Doesn't matter. The North Atlantic current passes, you see the arrows here, the water is going pretty much everywhere across the seals between Iceland and the Faroe Islands and the Shetlands. So we need to be a little tricky, and this time the authors, Rosby and Shafik, they used again the thermal wind equation, and they used the historical data. You see there were many, this is the blue dots over there and the red dots over there. And those data are interesting because there are not so many eddies in those areas, and so there are questions. But so by studying the balance between both regions, they were able to have an integrated transport of the upper branch across the seals. And I found their result fascinating because they found a very good correlation with the Atlantic multidecadal index, variability index, which is in black. You will see later what is this index. It's an index based on SST, and I'm sure Juliette will talk about it a little bit. But I don't have time to talk about everything. But it's an important index for the MOC, as you will see. But I'm talking about observations. So we have now for the MOC two new networks. One is at 26 North since 2004. It was already, you already saw it. So it's maintained, it's very, very expensive. And but it's maintained by several countries, but mainly by the UK. And as you can see, it's composed of several moorings on the boundary layers, with big holes between the moorings, because, as I told you, thermal wind equation is used for what is between. And they have to add also the component links to the wind-driven circulation. Yes, something else I wanted to see is here, the meridional overturning circulation is easy to compute in Z coordinates, because you can see on the left that in depth coordinate, the lower branch is below the upper branch. So even if we measure the transformation, diagonal transformation of the water, of light waters into dense water, it gives the same results in depth and in density coordinates. So this is easier than elsewhere. And as I told you, because of the geostrophy, it's easy to get the mid-ocean flow that you see on the right. And I have to accelerate a little bit. So here is the time series of MOC. So this is the sum. I give you all the variability to see how complex it is. And this is the sum of the Gulf Stream. The Gulf Stream is measured by a cable in the Florida Strait. And it turns out to be pretty stable. Even if it shows some seasonal variability, it's pretty stable. Then it's the sum also of what we call the Ekman circulation, which is the wind-driven circulation. And then it's the sum of the upper mid-ocean, which is obtained by the thermal wind equation. As I told you, everything that is in between the boundary, in the interior of the ocean, away from the surface, away from the boundaries. And so the time series is here in red, and with a filter in black. And you observe that, fortunately, in 2010, they had a big drop, and the MOC actually got even backwards. And it was critical, because they were going to lose their money to maintain the moorings, and this accident saved their life. But it's still, as you can see, an accident. Although the MOC didn't totally recover since then. It begins to recover. But we know that this accident was mainly linked to the wind-driven circulation. But then this anomaly stopped, and we still see some weakening of the MOC, but the latest data shows that it's not significant. Well, hardly. It's a very small number. So we are in an MOC of which is around 17 Sverdrup here, 18 maybe. Then the new network of the MOC, the OSNAP array since 53 now. And it's been installed in 2014. Again, it's an international consortium, but this time this is led by the USA, and in particular by Suzanne Lausier, the coordinator. And the OSNAP array is along the red sections you see here. How much time do you have? 5 minutes? Okay. The red, and then what you see here is also composed mainly of moorings, but an originality is that it's also composed of gliders over the Hatton Rockall Plateau, which is in the middle of the western line. And in the subpolar gyre, we are obliged to measure the AMOC in density because the density lines are slanted, and so you cannot compute it in depth coordinates because it superposes, and so it cancels out. This is I stole it from the last meeting because it's not published yet. And this is the time series until July 2020. You know that we are obliged to recover the moorings, but we don't have the data in real time. That's the problem with the moorings. So we have to recover them and then process the data and then release the results. Here again, well, since 2014, it's not very surprising, but you can see a lot of you see a lot of variability, but no trend. And what was one of the main results of this network is that most of the transformation of light water into dense water is happening in the eastern part of the North Atlantic. I mean, east of Greenland. We already guessed it from the Ovid, the results we had at Ovid, but we couldn't assess it. So here is across the French-Spanish section. So it's only snapshots, hydrographic section. We go out at sea and we have only like a snapshot of 1 month out there. So those snapshots are represented by the light blue dots. And then you have, we were able, thanks to those points that served us as the benchmark, we were able to reconstruct the AMOC amplitude from the altimetry, so the ocean height, plus the Argo network. And again, using the thermal wind equation, as we always do, because we have nothing else. And this is the reconstructed index of AMOC validated by the points, because the points are totally independent. They are, it's totally independent measurements, so it's very important to have them to validate. And on this, we have discovered until 1993, but let's look at here. And we see that the mean amplitude is pretty much as rapid, a little higher than across OSNAP. And what is, you can see decadal, well, nearly decadal cycles. And what is interesting here is it's pretty much as deep convections. The AMOC amplitude increases slowly through years, and it drops suddenly within 1 or 2 years. And that's what I think, in terms of processes, is interesting. And we are working hard now to understand, in terms of seasonal and interannual variability, the link with the other networks. In terms of decadal variability, we have written already many things, but there are still a lot of questions about the seasonal variability and the interannual. Well, interannual, we have a specialist here. It's probably quite chaotic, but seasonal, why is it different? I don't understand. Then, in conclusion, as you saw, oceanography is a very young science in full expansion. We have 1 paper every 2 days. So the observation network, fortunately, is now mature to detect accidents, to detect really big signals, and it can help to warn for evolutions. Because we didn't see anything, but it doesn't mean that a bifurcation, we'll hear a lot about bifurcations later, bistable equilibrium. It doesn't mean that it cannot stop brutally. We don't know. Up to now, no trend is obvious. So it's like the man that is falling from the 50th floor. Everything is okay up to now. Today, the maintenance and optimization of this observation network is a fight of every day. And this is a priority, and the management of the databases are also a priority because we have 2 orders of magnitudes more data than before, so we need to get much more organized, and it needs a lot of cooperation for defining what are the metadata, how to store them, what is important, what is not, and so on. And we still have a long way to go to understand the processes that dominate the ocean dynamics and its response to climate change. And you will hear a lot of talks about the drivers, about what happened in the past, about the bistable equilibrium in the future talks. So I invite you to stay with us to know more about it. Thank you.